you're a math major and having them say like, oh man, I hate either, oh man, I hate math, or oh, I was really good at algebra. Oh. Right, there's that one.
My friend, when I told him I was a math major, he's like, no way, that's so cool. How many digits pi can you name? And I'm like,
yeah, so when I was when I was in grad school, the couple of my friends actually stopped telling people that we were grad students in math because they didn't want to. It's like we have the same beginning of every conversation is either, oh my God, I sucked at math, you must be so smart, or which is like, where do you go from there? It's like, thanks, I guess.
Do the plus one here.
The plus one did not exist. I took a bunch of graduate courses here, but the plus one program didn't exist yet. So the plus one program actually, so I taught graduate measure theory in the fall here, and I was shocked at how high level the class was. I hadn't taught a graduate class here, right? It was the first time I taught one, and I didn't realize that people coming out of the undergraduate degree, like when I was a student here, very few people took graduate classes. You just went to your PhD program, those of us that went, and everybody else was interested in becoming a computer programmer or getting a job. And so when I taught the math class, I thought, oh, I'm gonna go easy here because it's not a PhD program. Let me teach this PhD level class. And I got in there and I was like, oh, I don't have to go easy. Everyone here is really good. So I kind of put the pedal down and like we learned basically a PhD program level class in there. So I was pretty excited. So the 4+1 program I think is good, especially for those that want to go on and I guess it's weird, right? It's hard to say. There's arguments for taking it, arguments against. I think I have some students that are going into it that wanted to go to grad school but didn't get in, and that's a pretty good argument for continuing if you want to go to grad school and you don't get into a PhD program. But last time we finished with this. Now I assume that last night everybody went home and proved that the space of polynomials was a vector space. We're just going to assume that you guys all did that. So you proved on your own, you definitely proved that PF is a vector space. And you probably also proved that PF is finite dimensional. Because of course, every single person in here, if I turned around and pointed randomly at somebody and said, what is the definition of vector space being finite dimensional? Everybody in here would be able to do that. So what does it mean for a vector space to be finite dimensional? You don't have to give me the formal definition of the book. You can just give me the idea of it. They'll be equivalent. Yep. Almost.
The spanning set of whole space can be represented as finite.
That's the same idea that he just said. What only one piece you're missing here. Yep. Yeah, you said the same thing. The three of you have said the same thing now. It's all the right definition. I'm proud of you. But the piece of it that you need is that the spanning list, this might seem like a triviality, but it's a set of vectors contained in the space, right? So just to remind you, no, you guys all basically gave the right answer, right? But finite dimensional means contains a list of vectors is spanned by. Now you might argue logically, of course they have to live inside. How are you going to be spanned by things that don't live inside you? But you got to be a little bit careful with that. You can be spanned from the outside as a subset, right? So finite dimensional means internally you contain vectors that span you. Okay, so everybody knew that, of course. Mind you, but I just thought it would be a good idea. So let's talk about, okay, we're going to give this one, if I had a horn, I would play it right now. So now we're going to talk about the single most important idea in linear algebra. Okay. So what is it, by the way? Linear independence. The single most important idea in all linear algebra is arguably linear independence. So I want you to imagine that we have a list of vectors. So if we started with the list v1 up to vm, and let's suppose that I've got some vector v contained in the span of those vectors. Well, if v is in the span of those vectors, then certainly it must be the case that there exist coefficients so that I can write v as a linear combination of v1 through vm. That's what it means to be in the span, right? V is in the span means that there exist an A1 and A2 up to AM in the field that A1 V1 plus A2 V2 AM VM is equal to V. I can find, if I say this to say I'm in the span, means I can find coefficients to make that statement true. All right, now suppose we had two of those. What if there was another way? What if there was another way to write V? Right, so we've got one way to write V as a set of coefficients. What if there was another way? So suppose also that C1 V1 plus C2 V2 up to CM VM is equal to V. I mean, just because an exist statement doesn't tell me how many sets of coefficients make the statement true. It just says there's at least one. So now suppose I have two such representations of V. Yep.
How does that notation represent the
I'm not saying it is separate yet. I'm allowing the possibility that there might be only one, right? It could be the case that this is just the A's again. It could be the case that they're different. I'm saying, let's suppose that I have another representation. It may be the case that logically we can force the C1s to be equal to the A1s. Okay. So if we have a second representation and you subtract them from each other, you take this equation and subtract it from this one, you're going to get the statement A1 minus C1 V1 plus A2 minus C2 V2 up to AM minus CM VM, zero vector. Right? I mean, I haven't done anything. It's just like regular old algebra. I have an equation, I have another equation, I can just subtract. So what I've written here is a representation of the zero vector. This is a set of scalars that I can use to put in front of the V1, V2, and V3, and so on, that would make the zero vector pop out the other side. Does that make sense? Okay, now, if the only way to have chosen this representation was this, if there was literally one set of scalars that made this equation true, then that would force all of these to be equal to zero, right? If the only way to write V is with A1 to AM, then AI minus CI would all have to be equal to the zero scalar, because these would be the same. If this representation is the same as that representation, the only way to do it would force that to be true. Make sense? If there's literally just this way of writing down V, and I subtract V, this expression from itself, then of course you're going to get a list where every entry here is zero, because AI is equal to CI. Okay, now, on the other hand, so one way of looking at this is if each vector has a unique representation, then this equation will have zeros in front of it. On the other hand, if zero can only be written uniquely as 0v1 plus 0v2 plus 0v3, so in the other direction, if zero can only be written uniquely, then that's going to force these things to be equal. Yep.
The bottom thing I'm just saying that the list of A1 to AM is equal to the list of.
Yes. Yeah. That would say the coefficient lists are the same. So there's this two-directional relationship here. If this vector has a unique relationship, then that's going to say that, I mean, that gives you a way of representing the zero vector. And if the zero vector can only be written as a combination where there's zeros stuck in front, that's going to force all of these to be unique. right? If the only way to write 0 is 0v1, 0v2, 0v3, 0v4, and all the way out to the end, if that's true, then that means any two representations must have the same coefficients. So we have this two-directional logic here where we've seen this before, where the representations of 0, the uniqueness of the representation of 0 forces the uniqueness of representation of vectors as well. So the idea is if 0 is equal to 0v1 plus 0v2 up to 0vm is the only way to get 0 in the span of v1 to vm, then any other vector has a unique representation as well. If this is the only way to write 0, then any vector with two representations actually has the same representation. That make sense? Kind of what I'm driving at here? So again, we saw this when we were talking about direct sums, right? The sort of uniqueness of writing down a combination of vectors that made up 0. So this situation is so special that it gets a name. So I guess the big idea here is if 0v1 plus 0vm is equal to 0 is the unique way of writing. Oh man, that's terrible handwriting. Sorry, I got excited for a second. I'll continue to be excited, but let me go way slower. Is the unique way to write 0 in the span of v1 to vm, then any v in the span of v1 to vm has a unique linear combination v equals a1 v1 plus am vm. If 0 is represented uniquely, every other vector is too. That's going to be our definition of linear. Yep.
It doesn't hold true if like one vector is made uniquely. It has to be a zero vector.
See, okay, yeah, if a single vector has a unique representation, then that's not necessarily good enough, right? Because you can, yeah, we'll talk about that when we get there. So it's this is really an if and only if statement, right? It's if and only if in the sense of if every vector, if every non-zero combination is a unique representation, then 0 will as well. But you can go backward. The powerful way is to go backwards and say if 0 is uniquely represented as 0 plus 0 plus 0 plus 0, then it must be the case that every other vector is too. Okay, so when I say that something is the most important idea in all of linear algebra, this one, I knew a guy in grad school that for whatever reason had decided to tattoo himself with this definition. I would not advise it necessarily. That's something you need to do in order to remember it. If you can use your brain instead of your skin, I encourage you to do so. But
Any professors like claim he's cheating?
well, no, he got it after he took the class, right? He also had the axiom of choice tattooed on his collarbone. He's a weird dude. A list of vectors v1 to vn v called linearly dependent. Independent. If the only choice of A1 up to AM in the field with A1 V1 plus A2 V2 up to AM VM equal to 0 is A1 equals A2 equals AM, which equals 0. Again, this definition isn't chosen out of nowhere. It's chosen because if the only way to represent 0 is as a linear combination with zeros in front, forces every other linear combination in the span to be unique as well. Okay. So this one is going to come up so often in the proofs of the rest of the class that you'll be dreaming it by the time we're done with this. Okay. It is desperately, vitally important that you carry this definition around in your head. This is something you have to be able to use naturally. Okay, so with that definition, let's do some classic examples of probably examples that if you look into the corners of the closets of your mind, you might remember this from an earlier linear algebra class. Suppose that I tell you that V1 and V2 are linearly independent. I say like not linearly independent. Not linearly independent. Can we say anything about their relationship? So to be not linearly independent would be to say that there are choices of scalars that make 0 that are non-zero, right? That there's some non-zero choice. Another one of these stupid definitions. Linearly dependent is not linearly independent. The idea here is when you think of linear dependence, you think I can construct 0 with non-zero scalars. Not all of them have to be non-zero, but at least one of them has to be non-zero. Probably, yeah, at least one. Does that make sense? Okay, so I got two vectors that are not linearly independent. What would that mean? Well, it would mean, again, okay, this is the response. This would be like you go to the doctor and they hit you on the knee with the hammer and your leg kicks or whatever, the reflex test. You see linearly independent show up in any guise at all, in any statement, and the very first thing you should do just by reflex is write this down. Not even any thought, just, oh, well, I got to use that. This is going to be used somewhere in this. You probably got a 90% chance of being correct. Okay, so what would it mean to say? What would it mean to say that V1 and V2 are not linearly independent? What can I say about A1 and A2? Yeah, okay. If we assume that V1 and V2 aren't 0, right? So we can add that. And V1 and V2 are not the 0 vector. Then yeah, A1 can't be 0. And also probably A2 can't be 0 as well, right? Because if they were, if this was equal to 0, then that has to not be 0. But the only way that would work is if this was 0. Yep.
Why can't we say that we want to do 2?
Oh, we're gonna consider the case of the 0 vector in a separate question. Suppose they're not. I give you two vectors and I say that I can do this. I'll give you an example. There's two vectors that are, I could make their span. They're not linearly independent. This is a linearly dependent set. What do you notice about those two vectors? One is a scalar multiple of the other one, right? I mean, this is 1, 1. This is 2 times 1, 1, right? So the idea that this is a scalar multiple of this can actually be proven from this statement. So classic exercise that shows up on exams would be assume that V1 and V2 are non-zero and linearly dependent. Prove that V1 is a scalar multiple of V2. That's what this exercise looks like, completely separate from any of the definitions, right? Assume V1 and V2 are non-zero and linearly dependent. Prove that one of them is a scalar multiple of the other. That's kind of the lead. When this shows up as an exercise or an exam problem, this is the way it shows up. Why do you need to know what linear dependent and linear independent mean? Because all you're going to get is the term, right? So when you look at an exercise like this, you have to be able to interpret what it means. The difficulty here is not usually in the algebra once you've got the statement written down. The difficulty is in figuring out what to do with it. So one approach to this exercise would be say, okay, I've got linear dependence or linear independence. I'm going to write down the equation A1 V1 plus A2 V2 is equal to 0. They are linearly dependent. That means at least one of A1 and A2 is not 0. But if V1 and V2 aren't 0, then the other one can't be 0 either. Right? If this one was not 0, and this vector is not 0, and they're somehow going to add up to the 0 vector, this scalar also can't be 0, right? With two vectors, these things both have to be non-zero. Statement 1. Actually, both A1 and A2 are non-zero. I'm going to leave that to you to think about for a second, right? The two vectors that are non-zero, if they are linearly dependent, neither scalar could be 0.
Are you saying that like the at least part? So you're like giving the least amount of information and then we try to conclude from it?
It's not that, it's the way the definition of linear independence is set up. Linear independence says all of the scalars are 0, right? If you negate that statement, you don't get all of the scalars are non-zero. If I say, what is the logical opposite of all scalars being 0? It's at least one of the scalars is non-zero. So the logical opposite of everything being 0 is at least one thing isn't. Right? And that's why I'm saying here, right? Linear independence is the logical opposite, the logical negation of linear independence. And so we go from all scalars being 0 to at least one of them isn't 0.
And then in actuality are like at least 2 always?
No. We'll talk about why. It's because the 0 vector could be part of a set of vectors, really. Because there's another exercise here, which I'm going to say, which is, this is another classic. Any set of vectors that contains the 0 vector is automatically linearly dependent. Right? That's a classic linear algebra exercise. Okay, so this idea again here, I'm trying to show you guys a baby idea of how linear dependence gets used, right? I give you a statement, you write down the equation, then you just manipulate it. Somehow we have to conclude that these things are both non-zero, and then as soon as you do that, you can just solve it for V1, right? If A1 and A2 aren't 0, you can divide by them. So you get V1 is equal to minus A2 over A1 V2. Subtract the A2 V2 to the other side, divide by the A1, which you're allowed to do because it's not 0. You're done. You don't even need to know both of them are non-zero. This works even if they aren't. You just need to know one of them isn't 0. Pick A1 to be the non-zero one. I'm allowed to divide by it. So what is the logical structure of a linear independence, linear dependence argument? They all look like this. You start with some condition. Something says linear dependent or linearly independent. You write down an equation and you manipulate it to extract the result that's asked for. Okay. Pretty common proof structure. Yep.
So the reason you write that sentence, at least one of A1 and A2 is not 0, because
This is true. So this is what linear dependent means. Linear dependent is the logical negation of linear independence. So one of the scalars can't be 0. I can find a way to do this where one of the scalars isn't 0. Another exercise I'd like you to think about. Again, classic. I think Axer does it, but don't cheat and look at his proof of it. This is an exercise to think about. You need something to do with dinner tonight. Any list of vectors, any list containing the 0 vector is linearly dependent. That's not hard to see, but you might want to practice writing it down, right? Like a good argument that that's true. Any list containing the 0 vector is automatically a linearly dependent set. Okay. All right. So again, lurking in the back of your head for the rest of your mathematical careers. I want you to have this. So leave that there. I don't know if we're going to use it again today, but I was leaving. We're going to do this by osmosis. Go to sleep on your math book. Yep.
It's sufficient proof of set of vectors is linearly dependent by just showing that one vector is a linear combination of all the others.
Yes, actually, that is the precise way to do it. So, okay, here's a question. This is a good question here. So here's a question. If V1 up to Vn is linearly dependent, is every vector in the list a linear combination of the others? What you just told me was one vector is a linear combination of the others, right? Which is true. In a linearly dependent set, one of the vectors will be a linear combination of the others. My question is it true for every vector in the set that every vector in the set is a linear combination of the other vectors? There's a question there you should think about, right? So what I'm saying is, okay, something in this list can be written as a combination of the rest of them. Is it true that V1 can be, and V2 can be, and V3 can be, and V4 can be, and so on? Okay, so put that in the back of your mind. I know some of you already know the answer to this, or you've intuited it.
Can like the constants be anything? Or like, do they have to be non-zero?
What do you mean?
I guess I'm thinking of an example of like where that fails, but I don't
So
know.
if you can, one of the constants has to be non-zero. The only restriction is one of the constants has to be non-zero.
Oh, because then that would be.
At least one.
Yeah.
Right? Okay, so I want you to, again, the point here is that like your previous version of linear algebra was very computationally focused. And I want you to sort of be thinking about what these ideas imply, right? What is it we're carrying around? Linear independence implies all kinds of stuff about the structure of the vectors, but what does it actually imply? So I want you to like probe the ideas that we're coming across here. Like, okay, so if we're talking about linear dependence being attached to these like products, scalar products, is that always what a linearly dependent set looks like, no matter how big it is? It's worth taking the time to think about that. Okay. Okay, right, so here we've got an extremely useful result, which is Axler calls the linear dependence lemma. And so the content of the linear dependence lemma is, if I have a linearly dependent set, I can always find a vector in that set that I can boot out and keep the span the same. So let me give you like a concrete example of what I mean by that first, and then we'll prove that it holds generally. If you had the vector v1 is 1, 0, 0, and v2 is 0, 1, 0, and v3 is equal to 2, 2, 0, the span of those vectors is the set of all points that look like x, y, 0. You can make anything that looks like x, comma, y, comma, 0. You can't put anything in the third slot because there's a 0 there in all these vectors, right? Also notice that this vector is a linear combination of these two vectors, right? v3 is equal to 2 times v1 plus 2 times v2. First off, why does the fact that v3 is a linear combination of these other two force this set to be a linear dependent set? Why is that true? If v3 is equal to 2v1 plus 2v2, which it is, why does that mean the set is linearly dependent? Subtract v3 if you're, so yeah, you got to subtract v3 first, right? Remember, linear dependence we think of as being representations of the 0 vector, right? If you can ever do this, you could subtract v3 from both sides and you get 2v1 plus 2v2 minus v3 is equal to 0, you've just found a non-trivial linear combination that makes the 0 vector, right? As soon as that means right there, the fact that you did that, you found a non-trivial way to write 0. v1, v2, v3 is linearly dependent. So it's a linearly dependent set. Here's what its span is. So the point of the linear dependence lemma is the observation that, well, this vector isn't contributing anything, right? Anything I make out of v1 and v2 already includes anything I can make out of v3. I'm not adding any new information with v3. v3 is already in the span of v1 and v2. So it turns out to be the case that if I find the vector that is the linear combination of two of the others, I can just toss it out. And I haven't changed anything about the span of the set. This already was a linear combination of these guys, so it's not contributing anything to the span. Yep.
That vector you boot out is still is the number of the span. Like,
It's still, that's right. I booted this out, but any combination of this is still in the span because it was built out of these two. Okay. And the point of the linear dependence lemma is I can always do this. If I have a linearly dependent set, I can always find some vector I can kick out without changing the span. Right, so this is the general setup here. So the lemma says the following. Suppose V1 up to Vm is a linearly dependent list. Then there exists an index J contained in numbers between 1 and m. All we're doing is saying something, we're finding a number that corresponds to one of the vectors in the list. Again, I'm replicating Axler's notation here. There exists an index so that 1, Bj is in the span of everything that came before it. I was saying this, right? V3 was in the span of V1 and V2. We find somewhere in this list, there's a vector that is a linear combination of all the vectors that came before. 2, if Bj is removed from the list, the span doesn't change. Which is exactly what we did here, right? We found a vector that was a linear combination of the previous vectors, and then we booted it out, but we haven't changed the span because anything I could make with V3, I could make with V1 and V2. So the lemma says, linearly dependent list, you can find some index so that there's a vector that corresponds to that position in the span, or in the span of the previous parts of the list. And then if you remove it, you don't change the span. Yep.
Is that important when it has to be from a previous part of the list?
It's a way to make sure that this process terminates. What you want to do is you want to set these things up so that, like, especially Axler's approach is he likes these algorithmic proofs. And so what he's going to say is, this is a way of saying, like, of giving you an actual algorithm you could code with a computer. He's saying, find the first thing in the list that's a linear combination of everything that came before, and then boot that out. Now, if you do it again, you could scroll down. If you still have a linearly dependent set, now scroll down the list and find the next one that's the combination of the previous ones and boot that one out. So he's setting this up in a way that you could apply it repeatedly. Yep.
Does the ordering really matter?
No, actually, it doesn't. Not at all. For us, I mean, lists are ordered, but the way that you think about this list. So later on, when we start talking about coordinates, the order of these things will matter because coordinates go with, like, when we have the idea of a basis, that's going to matter. Like the order of a basis matters when you start writing coefficient or coordinates down. But for this process, it doesn't matter at all. Right? And there's not even really a natural way of thinking about how to order vectors. I mean, you could try to order them by size, but what if they're the same size? Right. Also, you notice nowhere have we talked about what it means for a vector to have magnitude yet. Right? Like we have none of that. We don't even see magnitude of vectors until we get to inner product spaces, if we get there. Okay. So let's do this proof. Okay, so is it clear what's going on here? First off, like this, now again, this is where sort of a key tool is that any linearly dependent set can be reduced. And if I reduce them repeatedly, then I will eventually, hopefully, end up with a linearly independent set. Question.
Oh, I just,
What word is?
no.
Oh,
For part 2 of it.
yeah.
Why did you say, like, if the J in the list is spanned, change, why is that true?
Why is it true? I mean, the reason it's true is the same reason it was true here. If it can be written as a linear combination of everything that came before it, it's not actually contributing
Okay.
anything new to the span, because anything that Vj could do, these vectors can also do, right, is the idea,
Yeah.
right? Another way of thinking about it is, like, and we're going to use this idea, if you have, say, V1, let's just do an abstract list like this. And let's suppose we apply this lemma and it turns out V3 is the one that can be written as a linear combination of V1 and V2. Well, we could have written this list as V1, comma, V2, comma, A V1 plus B V2, comma, V4. If I start making linear combinations of these guys, no V3 shows up anywhere in the linear combinations, right? And so it would be okay to just throw V3 away because it's already only doing things V1 and V2 can do. Right, that's kind of what's going on here. We find the one that's the multiple or the span in the span, and then we say, oh, well, then we didn't need it because we're making all possible linear combinations, and we can do that just with V1 and V2. Yep.
Why doesn't our list go to the end anymore?
Because it may not be the case that the vector shows up at the very end of the list. In this one, V3 is the vector that is the combination of the previous ones. And we're trying to do this in a well-defined way. So we're saying, as you go down the list, there might be 6 vectors that are linearly dependent, or 1,000 vectors that are linearly dependent. Just pick the first one according to whatever index you've set up. Yep.
So if you remove Vj, then both the new sets of spans will span the same space?
Yeah, it doesn't change anything at all. The set of possible linear combinations of this space, if this is true, the set of linear combinations of this will be the same as the set of linear combinations of this. Throwing V3 away doesn't actually change anything about the possible linear combinations because I already have linear combination. V3 doesn't do anything new. Yep.
In our example, we had the 1 0 0 0 1 1 2 2 0.
Yep.
Could we not also throw away one of the other vectors?
You can. Yeah. No. Absolutely. In a set of 3, there's inside any linearly dependent set of vectors, there's lots of relations where things are combinations of other things, right? And so the idea is, how do you pick which particular thing to throw away? So if one dependence exists, there's going to be a bunch of them, right? It may not be every vector is dependent on every other vector. Like if you have 1 0 and 0 1, those will never depend on each other. But any other vector is going to be a combination of those two. And so the idea here is just pick one of those dependencies and throw it away. And then if you want to apply the theorem again, then go back and check to see, did that make a linearly independent set or not? Right. So this is intended to be applied iteratively. Okay. Good to say, man, this is a intensely interrogative class and a really good, no, in a good way. Like, teaching these classes to a bunch of silent people is terrifying. So it's everyone understands, and everyone looks at me like this. I'm not making fun of anybody who's doing that to me, by the way. It's just when everybody does it, it's sort of, it makes me work even harder to try to engage people. Okay, so let's prove this one. Actually, how much time do we have? Oh, we got plenty of time. All right. Since V1, Vm is linearly dependent, there must exist an A1 up to AM in the field so that not all of the AIs are 0 and A1, B1 up to AM, BM is equal to the 0 vector. So to say linearly dependent is to say that there exists some non-trivial linear combination of vectors that coughs up 0. Right? Okay. So here's the let J be the largest element of 1 up to M. So the largest thing in the list that's actually a non-zero coefficient, because we're going to divide by it. That's the game here. Find which of the coefficients is the biggest non-zero coefficient. So let J be the largest element of the list 1 to M, so that AJ is not equal to 0. Right? That's a very concrete way of choosing the AJ that we're after. Okay, so if AJ isn't 0, that means that you can write VJ as minus A1 over AJ V1 plus minus A2 over AJ V2 minus AM over AJ VM. Does that make sense? We're saying if it was the case that AJ wasn't 0, it was the biggest non-zero coefficient, take that vector and stick it on one side of the equation and then divide by that AJ, which I'm allowed to do because it wasn't 0. So what that means is, well, that's a proof right there that VJ is in the span of, actually, if it's not 0, it doesn't go all the way out to M. Yeah, that's right. That make sense? So far, anyway?
What were you saying that proves VJ?
This gives us VJ as a linear combination of the things in the list, right? And in fact, because it's the largest non-zero element, we can actually say more than that. Everything that came after it was 0, right? Every coefficient that came after this coefficient in the list was 0. So you imagine you have A1, you have A2, ... Here's AJ. You have, before it came AJ minus 1, AJ plus 1, up to AM. But if this is the largest, if the J here, if this is the furthest to the right in the list that's non-zero, everything that came after it was 0, right?
Why?
Because we said pick the thing in the list that's the biggest, that's the furthest out, that is non-zero. The J that we chose J, so that we chose the largest J in the list of indices from 1 to M with AJ not 0. Yep.
Is that AJ not 0? Is that 8 times J is equal to 0?
No, A sub J. It's just the index. We're choosing the index. I've got this list of coefficients. Some of them might be 0, some of them might not be, right? We know that because we have this, we have a list of coefficients, not all of them are 0. Maybe none of them are 0. Maybe some of them are 0. What we say is find the biggest thing in the list so that it's not 0. So we're a bit like it's like if I have a list of numbers that goes 1, 0, 3, 0, 0, 0. What's the position that's furthest to the right that's non-zero? Well, it's the third position, right? If you had this list and you were trying to choose J, you would choose 3 as the J. A4 would be 0, A5 would be 0, A6 would be 0. Does that make sense or no? Right, this is just a way of making this absolutely concrete where there's no wiggle room for how to do it. Pick the thing furthest to the right in the list that's a non-zero coefficient. So everything after it in this expression is 0. What have we just shown? Well, we can say more than this. If everything that came after J, if it came after AJ is a 0 coefficient, this is actually saying this. Because every other number that came after the AJ is a 0. So there is no rest of the sum. It just stops right there. Okay? There's a subtlety in the argument that's like, I'm taking time on this because Axler kind of like just blows through it. Yep.
Sorry, you said that everything after AJ is 0, which means that AM is 0?
Yes.
You're
Perhaps.
dividing by AM on the right.
It's just, I'm
side.
supposed to be divided by AJ.
Oh, okay.
This is supposed to be AJ.
All right.
Professor,
Yes.
can you explain that list again? Like, is that how we define list? Like, why is that?
Okay. Suppose I've got a set of vectors that are linearly dependent, and I can write that down, right? Concretely, I can write that down. What is AJ in this scenario? Well, A1 is 1, A2 is 2, A3 is 3, A4 is -6, A5 is 0, and A6 is 0. What's J?
4.
4. J is the index of the largest non-zero element, right? J is 4 because A4 is not 0, but everything past 4 is. So that means this sum could really be thought of as just 1v1 plus 2v2 plus 3v3 minus 6v4. I don't need to think about these terms up here because they're not there. There's 0 stuck in there. Then take the vector attached to that biggest thing, leave it by itself out here. Take that vector attached to the largest index that's non-zero, put it on one side of the equation, subtract everything else to the other, and then divide. Okay, do you believe that statement?
Yeah.
Okay, notice I have written V4 as a linear combination of everything that came before in the list. Abstractly, this is the same exact move. All I'm saying here is I have this list that goes A1, V1, A2, V2, up to AM, VM. One of these is not 0. Of the things that are non-zero, there's a largest one that's not 0. Call that VJ. Pick it. The list reduces to this. Because everything bigger than VJ was equal to 0. All the coefficients past this point in the list are equal to 0. That's what picking the J means. We shave off everything that comes after because they're all 0 anyway. Then VJ must be equal to minus A1 over AJ V1 minus A2 over VJ A2 dot 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 minus AJ minus 1 over VJ minus 1. VJ is a linear combination of everything that came prior in the list. Yes, it's also a linear combination of these, trivially, but who cares? They were just zeros, right? Okay, so right there, this proves we cut the back of the list where all the zeros are off. We show that we can, since AJ is not 0, I can divide by it. So VJ is in the span of every vector that came before. What's that? Oh, it's supposed to be AJ's. They're scalars. You're right. Yeah, I'm not dividing by vectors all of a sudden. Right? Okay. Well, that basically is the proof, right? I've shown that the VJ is a linear combination of every vector that came before it. It could be a linear combination of other vectors as well, but I don't care. And then what it remains to show is that the span didn't change. So we don't have time for that because I spent so much time talking about this. Yep.
But that span of everything before J does not equal the.
It doesn't equal the span of the whole space necessarily, right? All we've done is found one vector that can be built out from the things before. So that what we're saying is if I cut that one vector out, every vector that these covered, so like it covers the same thing with the VJ thrown in. So the completion of the argument basically is this idea where we take a vector out and replace it with this linear combination of everything that came before. The span will be in terms of this cut down set is the idea. So span won't change expressly because this vector is a linear combination of the stuff that came before it in the list. All right, so if I have time to finish this up next time, I will, which is, what is it? Well, it's Monday. Wow, I think they talk to you guys till next week. Okay, so this proof is important enough that you should read it, right? You should read this argument. The reason that we got stuck on this so long is because this is sort of, oftentimes in Axler's proofs, his proofs are nice, but there's these leaps in here, right? He just says this. He doesn't go into the logic of why it works, but you should probe his arguments. He makes leaps sometimes that he doesn't explain. So make sure that you nail down into his arguments and identify, okay, why is that true? If you want to know why something is true, ask about it. Okay? All right, get out of here. Thanks for your attention. Have a good weekend.
I just have a question on notation. Sure. When do we do like J is an element of like